Okay, so we're going to be learning about vectors and what we can do with them in this chapter or this module. And we're going to first start off with a scalar. So let's define a scalar. That's what we're used to thinking about. So definition. A scalar is a quantity specified in a single number. Okay, so anything like, so things like examples of scalars are things like length. I tell you how long something is, I just give you a number. I tell you what the temperature is, I give you a number. I tell you what the mass is, I just give you a number. I tell you what the height or weight is, again, just a number. Age is a scalar, just a number. So all these things are numbers, okay? So that's a scalar. So now a vector, all right? So a vector is a quantity and this thing possesses magnitude and direction. Okay, so it's a vector and it's directed by a line segment. So a vector is directed by a line segment. Okay, so I'm going to draw. So I can take and I can draw something that looks like this. That's a vector. I can start it at the origin. Uh-oh, I'm missing my arrow. Okay, let me draw my arrow in. Okay, so those are vectors. We can also talk about, when we talked about tangent lines, uh-oh, that's the wrong thing. I want that. I want this. So if I have a curve and you are driving around a curve, so let's say you are driving like this, and then coming right off of this, not that way, I want to draw it myself. It wants to draw it, I want to draw it. Okay, so that's like a tangent vector. So this is another vector, call that V. And so a vector V looks like that. Okay. So when you have a vector, it looks like AB. And let me check real quick the notation that is used by your book, which is they use, I still don't see it. Okay, yes, that's what they use. They use the arrows. Okay. So if I have this vector, so let's say I draw this. So I'm going to start at 0, 0. And if I go over 1, 2, 3, and up 1, so the terminal point is at the point 3, 1. So that is the point 3, 1. And then I draw my vector. My vector starts at the origin and goes and ends at that point. Then my vector V is the vector 3, 1. Okay, it goes to the point 3, 1, and it ends there. I can do another vector. So let's say I go -1, -2, 1, 2, 3. So this is the point, -2, 3. But when I take and I draw the vector starting here and ending at that point, then this becomes the vector, let's call it U. And it is -2, 3. So that's the vector. Okay. So a vector, so the vector notation, so we'll have a vector V, and it'll have a V1 and a V2 component. Okay. Or I may have a vector V, and I may call it AB. So it may have an AB component. All right, so let's define the magnitude or length of a vector. Well, that's actually not too hard to figure out. If I have a vector and it starts at the origin and goes to the point AB. So this vector V is the vector AB. That means I went A units in this direction and B units in that direction. So its length is to just use the Pythagorean theorem. Okay, so its length would be C. And so we call the length of a vector. And so we will have notation. Actually, again, I use changing books has been a little bit difficult, only because I've had to get to a different notation. Yep. Okay, we're good. So the length of the vector V is to take the square root of A squared plus B squared. So in other words, the length squared of a vector V is simply A squared plus B squared. Not difficult. et al. So for example, if I have the vector v, and v is the vector minus 1, 3, then the length of v squared is 1 squared, negative 1 squared, plus 3 squared, which is 10. So therefore the length of v is the square root 10. Okay. The 0 vector in other words, it's the vector that goes from the point 0, 0 to the point 0, 0. So the 0 vector, in a sense, is simply a point, but we do consider it to have a notion of vector definition. So here's our notation now. All right, so in the book, V might be bold, or you'll see V with a vector symbol over top of it. Another way they might define it, so that might be V, and that might be the vector AB. Another way they define it is sometimes in terms of these vectors IJ. So this might be AI plus BJ. And what in the world does that mean? Well, I is the vector 1, 0, and J is the vector 0, 1. So that is exactly what you see here. So of length 1, this is the vector I. So this is the point 1, 0. So this is the vector I. And it is 1, 0. And then this is the vector J. And J is the vector 0, 1, because this is the point 0, 1. Okay.
Yes, I understand.
Okay. All right. Definition. The two vectors U being U1, U2, and V being V1, V2 are equal provided their components are the same. So that would mean U1 would have to equal V1 and U2 have to equal V2. So that's what makes those two vectors the same, okay? Now something that's so the corresponding components are equal. Okay, so now two directed line segments Now you're saying, why didn't I use the word vector? Because I really want to say two directed line segments. So P going to Q, and let's say R going to S. All right, that have the same length and the same direction are equal. So what do I mean by that? Let's say I have something that looks like this. And so I go from here, 1, 2, 3, 4, 5, 6. So let's do that vector. Okay, so this vector, V, so V is the vector 3, 3. But if I move V over, and so now I go 1, 2, 3, and I go up 1, 2. Yep, that's right, 4. And then I draw this vector. And this vector is U. And U is the vector those two vectors are the same vector. I have to show you why in a minute. I can't show you yet, but they're the same vector. Even they're in the same direction and they're the same length. So they're equal. Okay. All right.
Okay.
All right. So how do you add vectors? The sum U plus V, all right, of the two vectors U, again being U1, U2, and V being V1, V2, is to just add them component wise. So this is the vector. So now we take U plus V and we draw a line over the whole thing. Okay, so this is the vector U plus V is U plus V, and it is to take U1, add it to V1, and then take U2 and add it to V2. All right, and the way you draw them is you start with, you take the two vectors and you make a parallelogram. So it's called the parallelogram law of addition. So it looks as such. So here's the vector V. and this is the vector u. So what I do is I take the vector u and I add the vector v to it. So this is u, this is v, and this is u. Uh-oh. So the vector u, so I start with u and then I add v. So that means I add v as such. So now I just add v by moving it over. Okay. Then I draw the parallelogram between the two, and I take the diagonal of the parallelogram and this green thing is the vector u plus v. Okay. So we use what we call the triangle law of addition. Sometimes we call it the parallelogram law of addition. And you can see why. Okay. So that's u plus v. Uh-oh. Well, how do you think I find u minus v? Well, we haven't talked about the vector. Oh, I better wait till I talk about the negative vectors yet. I ain't get that far. But I am going to use this picture again. Okay, so here's an example. So we have u is the vector minus 1, 3, and v is the vector 2, 5. Then u plus v clearly minus 1 plus 2 is 1, and 3 plus 5 is 8. So that's the new vector. Okay. All right. Here's a definition. Told you none of this is difficult. If u is the vector u1, u2, and c is a real number. In other words, it's a scalar. Then the vector c times u says take c and multiply by the vector u, but that's going to multiply each piece. So you end up with c times u1 and c times u2. Nice and simple. Example for u will be minus 4, 12. 1.5 u, it's going to be negative 1.5, 4.5, and pi u is going to be negative pi, 3 pi. Just that simple. It's 28. What in the world is 28? Okay. All right, so how does that change the length though? So let's see what it does. So I have the length now of the vector CU is now the length of CU1, CU2. All right. So let's do the length squared. I'm gonna do the length squared. So the length squared is going to be C squared U1 squared plus C squared U2 squared. And that is equal to C squared times U1 squared plus U2 squared. So therefore the length of CU is the square root of that thing. But that's just the square root of C squared times U1 squared plus U2 squared. So that's just the absolute value of C times the length of U. So when you multiply by a scalar, you just change the length of U by that scalar. So therefore, the length of C times U is the absolute value of C times the length of U. All right. Well, let's talk about negative vectors. All right, so the negative of the vector U is the vector negative U. So now I know how to find negative U because I know how to multiply it by a scalar. So negative U says just multiply U by -1. So that's just going to give me negative U1, negative U2. So negative U goes in the opposite direction as U. All right, but it has the same length. So negative U equal to minus U is in the opposite direction of U, and it has the same length. So here we have U. Then I have the vector C times U, which is just going to make it stretch. And then I have the vector negative U. Same length, opposite direction. All right, so let's talk about differences of vectors. All right, so the difference U minus V of the two vectors U equal to U1, U2, and V equal to V1, V2 is to take U minus V, but that is just, oops, U1, U2 minus V1, V2. So that's just U1 minus U2, minus V1, comma U2 minus V2. All right. So let's go back to my picture up here. Let's steal this picture again. Okay. It is hard being a perfectionist, child. Oh, I can't stand it. Ooh, it drives me nuts when stuff doesn't do perfect like I want it to. It will unnerve me. There we go. It's the best I can do. Okay. So now minus V is in the exact opposite direction as V. So here's minus V. Let me do minus V in gray. So minus V is in the exact opposite direction. It's the same length. So this is minus V. And so therefore, I'm going to draw from here to that point. And of course, it didn't start where I wanted to, but that's all right. I'll go back and fix it. This is going to be U minus V. Oh, I may not be able to go back and fix it. I think I'm done with that. Oh no, it'll let me. Uh-oh, maybe not. Yeah, there we go. Okay. All right. So just to make sure I know you're understanding this, I'm going to give you some quick problems to do. You got to give me the answers. Okay, so U is going to be 3, -2, and V is going to be 4, 6.
Can you go back up a little bit, please?
I can. Where do you want to go to here?
Yeah, just
Okay.
up a little more.
Up a little bit more?
Mm-hmm. Yeah, right there. Thank you. Okay, you can move down. I just took a picture.
Okay, so I want you to compute the length of U. I want you to compute U plus V. I want you to compute U minus 2V. And that's it. You get those right, I know you understand it. So I am awaiting your answers.
Okay. So for the first one, don't you just add the squares of both and then take the square root?
That's correct.
So it will be 9 plus 4, and then it's the square root of 13.
That's right. Okay.
Okay, look at the next one.
Okay, what do you get for the next one?
Trying to figure that out now. So you're just adding them since the
Mhm.
length of the vector u plus
Oh, you
the
don't
length,
know, no length, just add it.
just add it.
Yep,
So it will be 7
7,
and then 4.
4, good. That's it.
Okay. And then for the second one, you're actually, so it's pretty simple. So it's just algebra. So you just distribute the -2 to the 4 and the 6.
Mm-hmm.
So then it would be -5 -5, and then it would be -14.
That's it.
Oh, that's pretty
Okay.
simple.
And why did they drop the class off? Oh my gosh, I wish they didn't drop the class. It's such a good class. Oh my God, it's such a good class. Okay, let's refocus. All right, so now let's talk about a unit vector. A unit vector is a vector of length 1. Okay, so I can make any vector into a vector of length 1. All right, so this is how I will do it. I'm going to start with the vector. So let's let A be the vector. A1, A2. Then let's find the length of A. And then that is the square root of A1 squared plus A2 squared. And then we're going to define this new unit vector. And it's going to be A divided by its length. So my claim is the length of u now is 1. So if I take any vector and divide by its length, I get a vector of length 1. All right, well, let's see what happens. What does u look like? U looks like the length of A. I'm sorry. It looks like 1 over the length of A times the vector A1, A2. Okay? But that is the vector 1 over the length of A. I'm sorry, A1 over the length of A and A2 over the length of A. So that's the vector what U looks like. So the length of U squared is to take A1 squared over the length of A squared plus A2 squared over the length of A squared. Oh, I don't need the parentheses. But that's just A1 squared plus A2 squared over the length of A squared. But that's the length of A squared over the length of A squared, and that's 1. So since the length of U squared is 1, that implies the length of U is 1. So I can always make a vector into a unit vector. Okay. So here's an example. Find the unit vector in the same direction as A, let's say V, equal to 3, -2. Okay, so let's find the length of V. So the length of V squared is 9 plus 4. So that's 13. So that implies then the length of V is the square root of 13. So therefore U equal to 3 over the square root of 13, comma, -2 over the square root of 13 is a unit vector. In the same direction as V. Okay. Let's talk about some algebraic properties. Of vectors. All right, so I'm going to let U, V, and W be vectors. And I'm going to let alpha and beta be real numbers. Okay. First property, U plus V is equal to V plus U. So that's the commutative property of addition. Number two, U plus V plus W is the same as U plus V plus W. You know what property that is?
Reflexive or transitive.
Ooh, you thinking real deep. It's just the associative property. I can just move, yep, you thinking real deep. Did you take linear already?
I take it next semester. I took discrete though, and stuff like that.
Okay. Okay, so if I take alpha times U plus V, this is the same as alpha U plus alpha V. And this is the distributive property and this is of multiplication over addition. And if I have alpha plus beta times U, that is alpha U plus beta U, that's also the distributive property. But that's the distributive property of addition over multiplication. And number 5 is I can take alpha times beta and then multiply it by U, or I can take alpha and multiply it by beta U, or I can take beta and multiply it by alpha U. Okay, and that is commutative property of you can commute the, well, what is that? I think what that name is. Okay. So all that says is if I have U equal to 1, 3, V equal to -1, 6, and W equal to 0, 7. It says I can do U plus V and get 0, 9. And then I can do U plus V and I can add W. And then I'll get 0, 13. Or I can take V plus W, V plus W, and I'll get -113. And then I can add U to V plus W. And I'll still get that's not right. 9 and 13, it's 9 and 7 is 16. Okay, and then I still get 0, 16. I'm like, what in the world? Okay. All right, I'm gonna pause and go back and look at my goals for this section and see if I covered everything. Describe a plane vector, basic operations, express a vector in component form. We'll go back and do that. Explain the formula for the magnitude, express a vector in terms of its unit vector, and give 2 examples of vector quantities. Okay. Okay. So let's let V be the vector V1 and V2. We want to express V as a product of its length times its direction. Okay, so it's actually rather easy. We already said we can make V a unit vector. So the vector V over its length is a unit vector in the direction of V. So if I have a unit vector, but I want it to be as long as V, I'm going to take the length of V and then multiply it by the unit vector that's in the direction of V. So it looks like I haven't done anything, but I have. So let's go back to that vector V. I don't know, I don't know if it was 3 minus 2, but I'm just going to use 3, 2 for a moment. We know that the length of V, what was it?
3 minus 2.
Okay, so we know the length of V was the square root of 13. So therefore, we can write V, if we take the square root of 13, that's its length, and then we multiply it by 3 over the square root of 13, comma, and this should be a vector. -2 over the square root of 13. So now this is its length. And then this is its direction.
Okay.
You have a question?
No, I understand what you did. You did that up there too, so it was kind of like a follow-up.
Yeah. Mm-hmm. Okay. All right, do I talk about distance between the two vectors? Let's see. Okay, there are a few more properties I do need to cover. Let me, your section, your book does a couple of more properties. So let me do a couple more properties. The first property, it's actually only 1, 2, 3 that I didn't give you. Okay. Okay. All right, so we talked about the zero vector. So the zero vector has the property that u plus 0 is equal to 0 is equal to u, but that is the same as 0 plus u. So that's the zero vector. Then every vector u has an additive identity. So every vector u so that means u plus the opposite of u is the zero vector, but that's the same as the opposite of u plus u. And then multiplicative identity and that is the number 1 times u is equal to vector u. So those are the other 3 properties that I kind of took for granted. So I want to make sure that I basically give them to you. Okay. We didn't talk about the distance between 2 vectors yet. But I do, yeah. Okay, so let's talk about here's an example problem. So let's do the distance between 2 vectors. The distance between 2 vectors Not what I want to do. I want to do an example. I like this example too, because this one, I think of this example every time I do this problem. Okay. So you can use trigonometry to resolve a vector into its component parts. Okay. So let's say you have this vector. Okay. And this vector is V, and the length of V is 40. And I also want V to make an angle with the horizontal of 30 degrees. Well, if I drop a perpendicular, then I can use trig. And so I know that this side over here, I'm going to call V horizontal. And this side over here, I'm going to call V vertical. Okay, so now if I take V horizontal and divide by the length of V, I will get the cosine of 30 degrees. So that lets me know that this side down here is the length of V times the cosine of theta. And if I take V vertical and divide by the length of V, that is the sine of theta. So that says this side is the length of V sine theta. So once I know a vector and the angle that it makes with a horizontal, I'm able to break it up into its components. So now I can write the vector V as the length of V, the cosine of theta, times the length of V, I'm sorry, not times, comma, the length of V sine theta. So I can write V in terms of the length of its length and the angle it makes with a horizontal. And that is what we call taking V and actually separating it into its vertical and resolving it into its vertical and horizontal components. So this is V is resolved into its horizontal and vertical components. So an application of this you want to push a loaded supermarket cart. I think about this every time I go shopping. By applying a 20-pound force F that makes a 30-degree angle with the horizontal. Resolve F into its horizontal and vertical components. Okay, so here's the supermarket cart. And so here's the person pushing it. The force is going down like this. Onto the edge of this. And it's making a 30-degree angle with the horizontal. So this is 30 degrees. And I know the magnitude of the force is 20 pounds. Okay, so what I need to do is I need to figure this out. So 30 degrees is pi over 6. So I'm going to redraw my triangle for a moment. So let me redraw my triangle. Okay. All right, so this is 20 and this is pi over 6. So I know that this side is 20 times the cosine of pi over 6. And this side is 20 times the sine pi over 6. So this side is 10, the root of 3, and this side is just 10. But note that the force itself is going down. So therefore, its x component is going in the positive 10 to the root of 3 direction. So I can write the force but the y component is going down, so I have to write that in the negative 10. And if I was going to write it in terms of I and j, I would have 10 to the root of 3, the I component, minus 10 to j component. Okay. So the negative is the force points down. Okay. Any questions about that?
No.
Well, we're good because tomorrow, if you have any questions about the test, you can ask me. I can tell you right now, let me stop this.